Okay, now we will see how to solve the problem on trusses. And this is a given problem. For the truss shown in figure, determine nodal displacements, stresses in each element and reactions at supports. Considering A is 200 mm square and Young's modulus of the material given is 70 GPa. Now this is a problem given. So they are given initially node numbers. Okay, this is node number 1, this is node number 2, this is node number 3. So node number 1 and 2 will make element 1 and node number 1 and 3 will make element 2. Okay, now if you want we can write the coordinates for this particular thing. So for solving this problem, I will write first nodal data, so which is node number, x coordinate and y coordinate. We have 3 nodes, so node number 1, node number 2, and node number 3. So we'll write the nodal data for this. Okay, if we consider node number 1, this is a node number 1, the coordinates are x distance is 500 and y distance is 300. So you can observe here, this is the dimension given for x. So x is 500 and y coordinate is 300, that we can write here. X is 500 and y coordinate is 300, and since this is node number 2, the x coordinate is 0 for this and y coordinate is 300. X coordinate is 0 and y coordinate is 300, and that we can write here. X coordinate is 0, y coordinate is 300. Since this is node number 3, x coordinate is 500 plus 400, 900, and y is 0. We can represent that here. X coordinate is 900 and y coordinate is 0. And at node 1 we can have 2 displacement functions. Okay, so we'll have q1 and q2. X displacement will be q1 and y displacement will be q2. At node 2 we'll have 2 displacement functions. X displacement will be q3 and y displacement will be q4. At node 3 we can have 2 displacement functions, which is x displacement is q5 and y displacement is q6. Okay, and after this nodal data, we will write element connectivity table. So in this element connectivity table, we will have element number, initial node, final node, length of the element can be taken as LE, L, direction cosine L, direction cosine M, L into M, L square, M square. Okay. See, based on number of elements present, you can prepare this table. Since we have 2 elements here, so element 1 and element 2, so element number 1, element number 2. So for element number 1, if we consider this is the element number 1, see, for this initial node is node number 1, I will write node number 1, and node number 1 coordinates are 500 and 300, that is x coordinate is 500 and y coordinate is 300, I will write here. And final node, this is a starting node for element 1 and this is a ending node for element 1. So final node is 2 and its coordinates will be, node number 2 coordinates are 0, 300. We can represent that here, 0, 300. And similarly you can represent the same for element 2. And if we consider element 2, starting node is node 1 and ending node is node 3, and starting node coordinates are 500 comma 300 and ending node 3 coordinates are 900 comma 0. So starting node will be 1, ending node will be 3. Starting node coordinates are 500 comma 300 and ending node coordinates are 900 comma 0. So these are the initial node and final node for element 1 and element 2 respectively. And in order to find out length of the element formula used to find out length of the element is x2 minus x1 whole square plus y2 minus y1 whole square. Okay, now see, if we consider element 1, you can treat this as x1, this as y1, x2, y2. So now you can substitute for element 1 as these values. Now value of x2 is 0, x1 is 500 whole square plus value of y2 is 300, y1 is 0 whole square. And if we find out value of LE, so y1 is 300, so value of LE will be 500 for element 1. Similarly for element 2, okay, now I'll directly again we can take the same formula, x2 minus x1 whole square plus y2 minus y1 whole square. Now you can treat this as x1, y1, this as x2, y2. So now if you substitute these values, x2 is 900 minus, okay, now for this x2 is 900, x1 is 500 whole square plus y2 is 0, y1 is 300, 0 minus 300 whole square. Now if we find out length of the element, so length of the element happens to be 500, so we'll write that 500 here. And okay, now for element 1 we'll find out direction cosine L. L is equals to x2 minus x1 divided by length of the element. So now we have x2 is 0, x1 is 500 divided by length of the element is 500. So value of L will be minus 1, so we can write that value here. And M will be y2 minus y1 divided by LE. So y2 is 300, y1 is 300 divided by length of the element is 500, so it will become 0, M will be 0, and product of L into M is 0, L square is 1, M square is 0. Similarly for element 2, L will be x2 minus x1 divided by length of the element. Now 900 minus 500 divided by length of the element is 500, so it happens to be 0.8. Value of L happens to be 0.8, and M will be y2 minus y1 divided by length of the element. So y2 is 0, y1 is minus 300 divided by length of the element is minus 500, so it will be 0.6. So now value of L is 0.8 and the value of M is 0.6, and L into M is 0.48 minus 0.48, L square is 0.64 and M square is 0.36. Okay, now we will continue. So we know that stiffness matrix for a truss element is given by K is equals to EA by L, E L square, M square, minus L square, minus M square, sorry, this is L square into LM, M square, minus LM, minus M square, minus L square, minus LM, minus Ln minus m square plus L square Ln into m square. This is a stiffness matrix. Now if we consider for element 1, okay, since Young's modulus is 70 GPa, so 70 into 10 power 3, area of the element given is 200 mm square, so 200. Length of the element for element 1 is 500. I will take that value, and L square from the element connectivity table, value of L square obtained is 1 and value of m square is 0, so I will substitute that values here. L square is 1, L into n is 0, L into n is 0, m square is 0, so minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1, 0, 0, 0. And if we consider element 1 is made up of node 1 and 2, so its coordinates will be 1, 2, 3, 4, 1, 2, 3, 4. So if we simplify this, so I will keep the 10 power outside, so 10 power 5, 0.28, 0, minus 0.28, 0, 0, 0, 0, 0, minus 0.28, 0, plus 0.28, 0, 0, 0, 0, 0. Now this is a stiffness matrix for element 1. Again, for your reference, you can write the node number 1 and 2. These are the nodal displacements constituting element 1. So similarly for element 2, K to E element stiffness matrix will be 70, 10 power 3. Young's modulus is same, and length of the element is also same. Length of the element is 500. Now L square is 0.64, m square is 0.36, L into m is minus 0.48, and m square is 0.36, so this will be minus 0.64, minus 0.4 plus 0.48 plus 0.48 minus 0.36, and minus 0.64 plus 0.48 plus 0.48 minus 0.36 plus 0.64 minus 0.48 minus 0.48 0.36. So again, if we simplify this like the same way how we did for element 1, so element stiffness matrix for element 2 will be, so by keeping 10 power 5 outside, we can represent like this: 0.1792 minus 0.1344 and minus 0.1792 1344. So this will be minus 0.1344, 0.1008 minus 0.1344 minus 0.1008, so minus 0.1792, 0.1344, 0.1344 minus 0.1008, 0.1792 minus 0.1344 minus 0.1344, 0.1008. So since element 2, you can observe this element 2 is made up of node number 1 and node number 3. So while writing the displacements, it will constitute node number 1 and 2. So Q1, Q2, Q5, Q6. So that is the reason why we write 1, 2, 5, 6, 1, 2, 5, 6. Okay. Now we will write the global stiffness matrix. So global stiffness matrix K So 10 power 5, I'll keep it outside. So it will be a 6 cross 6 matrix. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now 1 cross 1. Okay, here if you observe, node 1 is shared by element 1 as well as element. So we'll have two values. 1 cross 1, we'll have one value here and one value here. So 1 cross 1 will be getting 1 cross 1 value as minus 0.4592, that is 0.1792 plus 0.28 0.1792 plus 0.28 is 0.4592. Again similarly 2 cross 1 also will have two values, 0 and 0 minus 0.1344. So 0.1344. 3 cross 1, so we will have only one value, which is minus 0.28. 4 cross 1 is 0. 5 cross 1 is minus 0.1792. 6 cross 1 is minus 0.1344. Similarly 1 cross 2 minus 0.1344, 0.1008, 0, 0. So 5 cross 2, 0.1344. 6 cross 2 is minus 0.1008. So 1 cross 3 will have one value here, and which is minus 0.28. 2 cross 3 is 0. 3 cross 3 is 0.28. 4 cross 3 is 0. 5 cross 3 is 0. 6 cross 3 is 0. And 1 cross 4 is 0. 2 cross 4 is 0. 3 cross 4 is 0. 4 cross 4. 5 cross 4. 6 cross 4 is 0. So 1 cross 5 will have 0.1792. This is 1 cross 5. 0.1792. 2 cross 5 is 0.1344. 3 cross 5 is 0. 3 cross 5 is 0. So 4 cross 5 is also 0. 5 cross 5 is 0.1792. 6 cross 5 is 0.1344. So similarly 1 cross 6 0.1344. 2 cross 6 minus 0.1008. 3 cross 6 is 0. 4 cross 6 is 0. 5 cross 6 is minus 0.1344, and 6 cross 6 is 0.1008. Okay, this is 6 cross 6 value. Now this is a global stiffness matrix. So now we'll transfer the global stiffness matrix into general description of FEM. KQ is equals to F. I have written global stiffness matrix. These are the nodal displacements Q1, Q2, Q3, Q4, Q5, Q6, and at node 1 the load in x direction can be taken as F1, in y direction can be taken as F2. So F1 is 0, F2 is 12 kilonewton, F3 is 0, F4 is 0, F5 is 0, F6 is 0. Now I'll use elimination method. Since node 1 is totally free, it is subjected to loadings, I'll leave node 1, first row first column I'll leave it as it is, and second row second column I'll leave it as it is. Since node 2 it is totally fixed, so I'll delete third row and third column, fourth row, fourth column, because each node will have 2 degrees of freedom, and even node 3 it is totally fixed. So I'll delete fifth row, fifth column, and sixth row, sixth column. So and we'll have only these 4 values, and if you solve for this either by using a matrix method or by using equations, we'll be getting the values for q1 and q2, the 2 unknown values q1 and q2. So value of q1 that we obtained is minus 0.571 mm, and value of q2 obtained is minus 1.952 mm. And obviously since node 2 and node 3 are fixed, so q3 will be equal to q4, which will be equal to 0, q5 which will be equal to q6, it will be equal to 0 mm. Now we will see how to find out reactions at supports. So now we have 2 supports, that is at node 2 and node 3. So R3 will be K31 Q1, K32 Q2, K33 Q3, K34 Q4 plus K35 Q5 plus K36 Q6 minus F3. So since Q3, Q4, Q5, Q6 are 0, directly this Q3 will become 0, Q4 will become 0, Q5 will become 0, this value also becomes 0. Since there is no load acting on node 2, even F3 can be taken as 0, and so K31 is 0.4592 into 10 power 5 into value of Q1 is minus 0.571 plus K31 is minus 0.28 into 10 power 5 minus 0.571. Since K32 is also 0, even this term will become 0. So value of R3 will be 15.988 kilonewton. Similarly, R4, K41 Q1, K42 Q2, K43 Q3, K44 Q4 plus K45 Q5 plus K46 Q6 minus F4. Since row 4 is totally 0, we can directly write R4 as 0, and R5 is K51 Q1, K52 Q2 plus K53 Q3 plus K54 Q4 plus K55 Q5 plus K56 Q6 minus F5. So R5 can be taken as, since phi 1 is minus 0.1792 into 10 power 5, Q1 is minus 0.571 plus phi 2 is 0.1344, this is K52, this is K51, 52 into Q2 value is minus 1.952. So value of R5 that will be obtained is minus 16.002 kilonewton. Similarly, R6, if you find out R6, that is K61 Q1, K62 Q2 plus K63 Q3 plus K64 Q4 plus K65 Q5 plus K66 Q6 minus F6. If we solve this equation, so value of R6 will be that will be obtained is 12.001 kilonewton, and this is about reactions at supports. And in order to find out stresses in each element. In order to find out stresses in each element, so sigma 1 is equals to E into B into Q. So we write E as it is. B is 1 over LE minus L minus M plus L plus M. Q1, so element 1 will have nodal displacements Q1, Q2, Q3 and Q4. So Young's modulus of element 1 is 17 to 10 power 3. Length of the element is 500. So the direction cosine for element 1, L is minus 1, so minus into minus it will become plus 1, M is 0, so this will become minus 1, 0, and value of Q1 is minus 0.571, Q2 is 0, Q2 is minus 1.952, Q3 is 0, Q4 is 0. If we simplify this, value of sigma 1, that is stress for element 1, will be obtained as minus 79.94 Newton per mm square. This is stress obtained in element 1. Similarly, stress for element 2 will be taken as E into B into Q. So E by LE minus L minus M plus L plus M. So now for element 2 it will be Q1, Q2, Q5, Q6, because at element Q2, element 2 is made up of node 1 and node 3. At node 1 displacements are Q1, Q2. At node 3 displacements are Q5, Q6. So that is why we have written like this: 70 into 10 power 3, 500. So length of the element is minus 0.8 plus 0.6 plus 0.8 minus 0.6. Similarly, minus 0.571 minus 1.952, 0, 0. And if we solve this equation, sigma 2 obtained will be 100.016 minus 100.016 Newton per mm square. Thank you. If you have any doubts, contact me on this number. Thank you.